Hello everyone, let's continue the discussion about the molecular geometry and polarity. We've been doing the steps of arranging the valence electrons in the molecule polyatomic ions. It's called the Lewis structures. And then we figure out the E-VSEPR notation, and we're trying to come up with the number of electron groups. And so now we're going to put everything together and start to determine what is actually controlling the shape, or the shapes of the molecules in polyatomic ions. So this section, this vodcast is about electron group geometry. In the previous vodcast, we discussed about this particular notation. If we have the correct Lewis structure for the molecules or polyatomic ions, you will have the ABXEY notation as indicated. A is the central atom, B is the surrounding atom, E is the lone pairs. It's lone pairs. It's those valence electrons sitting on the central atom that's not shared. That's not bounded or shared with the any surrounding atom. The X and Y are subscripts denoting how many of those surrounding atoms or the lone pairs. As we can see, those are examples for carbon dioxide. You can write the correct Lewis structure will be indicated. It's shown here, and this will be the AB2E0. There will be two surrounding atoms bounded with carbon, so it's two electron groups, but no lone pairs. So the total number of electron groups will be 2 for methane. It will be AB4E0. Total number of electron groups will be 4. And the list goes on. Ammonia, you'll have 3 bonded, so the AB3. Now you'll have a pair of unshared valence electrons on the central atom, nitrogen, and in this case it will be the AB3E1. Total number will be 4. Water will be AB2E2. Total number 4. The phosphorus pentachloride, it will be AB5E0. Total number 5. Sulfur hexafluoride will be AB6E0. Will be 6. So the X plus Y is the total number of electron groups on the central atom. And further extended out, those are the examples. Boron trifluoride will be AB3E0. Total number of electron groups will be 3. BRF5. Bromine pentafluoride. And now, after finishing the steps about Lewis structures, you have 5 surrounding atom bounded with the central atom, plus one lone pair of valence electron that's not shared. That's not bounded with any of the fluorine, so it's sitting on the central atom bromine. So this is AB5E1. Total number of electron group is 6. Same token, this is polyatomic ion IF4. It's minus charged. Now you'll have two pairs of unbounded valence electrons in the central atom, iodine, and this is AB4E2. Then will be the total number will be 6 electron groups. And it will be interesting. And now let's talk a little bit about what is the nature of the interactions between those electron groups. So if I have a central atom, and now I have electron groups surrounding it, and in this case I'm drawing 4, I can draw 2, but what would be the interactions? What would be the interactions between those electron groups on the central atom? So here comes, and you can take a closer look at those electron groups. Either they contain what we call it bonded valence electrons, because those are the bonds shared between the central atom and surrounding atom. If I have a central atom and if I have a surrounding atom, that we'll call it A. So those are the bounded, each bar representing a pair. You can have double bond, that would be 2 pairs, triple bond would be 3 pairs. So those are bounded valence electrons. Or you'll have situations and it's just a pair of unshared, or sometimes referred to as unbounded, or sometimes also referred to as lone pair of valence electrons. So now you start looking at it, all those electron groups, either they have fully bounded electrons or the lone pair. As we indicated, you learned it before Pauli exclusion principle, there was no way to introduce further electrons onto those electron groups. And as you notice, they are all negatively charged. They are all negatively charged. So the interaction between the electron groups strongly repel each other. They repel each other because first they're all negatively charged, all negatively charged. Second, each group cannot accept additional electrons, any kind of electrons, valence electrons in particular. So this is actually forming a very simple but elegant theory, or the means to predict the shape based on this strong repulsion between electron groups. So it actually has a name for it. It's called Valence shell. Oh, that's not to do that. It's called the valence shell electron pair or pairs repulsion. So it takes the whole first letters, valence shell electron pair repulsion. Valence shell electron pair repulsion, commonly known as E-VSEPR theory. So this theory is solely based on repulsion between electron groups. It's solely based on the repulsion between the electron groups. Since they repel with each other, so they want to maximize the distance between the electron groups. However, they cannot totally fly apart, fly away from each other because they are connected on the central atom. Okay, so remember the electron groups are all connected on the central atom. And how actually it works. And there's a great simulation program on the University of Colorado website. And here's the link. You can actually click on it and go there. Just be careful, it's Java based. Let me show you the website. Okay, let me show you the website. Here's the FET. Here's the FET website on the University of Colorado, and the interactive simulations. Be careful, this is a Java-based program, and please, if you go to the website, you can read the security advisory. So for Java, the best way is download it to your local hard drive and run it from there. Do not run it through the web browser. And I already installed it on my computer. Let's run it and take a look at how it works. Okay, so here we have a central atom, and let's use the lone pair to excuse me. Let's use the lone pair to represent electron groups. And the thing really I like this simulation is actually give you the flexibility to add and to play with it. It's totally interactive. Let's add 1. So there's a 1, even though it shows here as a pair, but it could be double bond, triple bond. So add 1. If I add another 1, and if I start dragging this, if you actually can click on it and start dragging it. If I try to drag them closer together, you can see how the other one respond. Because it has a very strong repulsion between those groups. So the best way to minimize the repulsion is try to keep them as far away as possible. If you have 2 electron groups, what's the best way to keep them as far away as possible? And here will come about that geometry. For the electron group geometry, if you have 2 electron groups, linear will be the best way. Linear will be the best way. Okay? If I add another electron groups, pause a little bit to think what will happen. It will happen like that. Again, if I want to drag them closer to the other will respond because of the repulsion between those electron groups. A very strong repulsion between those electron groups. Okay? So now you can actually see the geometry of if you have 3 electron groups. It looks like equilateral triangle is on the plane. So this one is actually called trigonal planar. Trigonal planar. If I add in the 4th one before I add it, you can pause and start think about it. How am I actually going to maximize the distance between those electron groups? In this case, you have to get away from the 2-dimensional. Now you go to the 3-dimensional space. If I add another one, you can actually see trying to maximize the distance between those. Same thing, if I move one, actually the other one be pushed away. But the best way to look at it now is to have a 3-dimensional structure. We call it tetrahedron. So you can see these 2 kind of electron groups are pointing outwards, out of the screen, and these 2 pointing inward, inside, towards the inside of the screen. So now this is a 3-dimensional space. This is in a 3-dimensional space. It's called a tetrahedron. Okay, let's add another one, and now you have 5. Now you have 5 electron groups now. And as you can see, if I move it around, and the other one will be responding because they repel each other. Now you have a shape, and now it requires some of your really good knowledge about 3D geometry. As you can see, this 3 groups are on the same plane, and now you have this two groups is looking like a stick going perpendicular right through it. So this one, the one behind, and this one forms an equilateral triangle, and with these two going right through it. And if I rotate it, you can see it much better. Okay, so those one, the one behind, the one in the front, form an equilateral triangle, and this one's going through, right through it, going right through it. Okay, so if I can move this around, so this is actually called trigonal bipyramid. Why do I call it a trigonal bipyramid? Is actually, this is a pyramid. If you're linking all those points, apex together, it's a pyramid with a triangle base. But why it's called a bipyramid? We have a pyramid on the top. We also have the pyramid on the bottom. So this is for electron group 5. And we add another one, you will have electron group. The number of them are 6. As you can notice here, it's getting fairly crowded. And if I drag one, the other one will respond because they repel each other. So the best way they can do is to assume this geometry. As you can see, if I put it this way, you can see much better. So now you actually have a square plane on here, and now you have a stick going through it. So now you have a total 1, 2, 3, 4, 5, 6 electron groups. So those are the ones. It's very interesting, and I would strongly advise you to download this simulation onto your local computer, open it up with JavaScript, and play with it. So if I can start, say, taking one out, if I can take one out, now it becomes 5, and you can see it becomes less crowded, and the angle starts to increase. This one will be a trigonal bipyramid. If I take out another one, you can see this is becoming a tetrahedral. It's becoming even more relaxed. Take out another one, trigonal planar, and take out another one. Now you relax it back to the linear shape. So let's switch back to the presentation, and so to reiterate, the valence shell electron pair repulsion theory, it's very simple. It's based solely on the repulsion between the electron groups. So those electron groups trying to maximize distance between them because they are connected on the central atom. They're part of the central atom. So for that, it influences the shape of the molecule. So let's revisit if you have total electron group 2, you'll have a linear shape, and sometimes we actually draw it like this. Or X, 2 sticks representing that. So if I have 3 electron groups, you notice from the simulation, we'll have a trigonal planar. Sometimes drawn like this. It's equilateral. In between here is actually 120. In between here is actually 180 degrees. Okay? Or you use X. But if you have 4 electron groups, now you have what we call the tetrahedral. I will have a tetrahedral. We're drawing like this, X like this. You use a solid shade, and you use a dashed shade. So the angle here is becoming smaller, 109.5 degree. Or we draw it as alternatively, we draw it this way. It is important you learn that. So this is actually the way to use a 2-dimensional graph to represent a 3-dimensional shape. This this stick, and this central atom is on the same screen, the plane of the screen. So now you have one electron group is pointing outwards, is pointing away from the screen, and the other one is pointing towards the screen, okay, towards the inside of the screen. So this one is for the tetrahedral, and if you have 5 electron groups, now you'll have a trigonal bipyramid, and we usually draw it in this way. They're on the same plane. Now we have one going inside, the other one's coming out. And if we have 6, we'll have what we call octahedral. We carry octahedral, and you can have X, one this one this one, and the one on the bottom. So now you'll have one going inside, the other one going outside, the other going inside, the other one going to go to the outside. So those 4 are on a square plane, and this is going directly through it. This is on equilateral triangle, and with the other 2 going perpendicular right through it. The reason why it's called a trigonal bipyramid, if you link those sides together, it's a pyramid. It's triangle based, so it has 2. One's on the top, one's on the bottom. So it's called trigonal bipyramid. And now this one. Why this one is called octahedral is because this is a square. This is actually a pyramid, but I have 4 sides. You have 4 triangles to cover it, and you have 4 on the top, 4 on the bottom, so you have 8. So to form the shape of this, it will be octahedral. It will be octahedral. So to kind of recap what you learned in this podcast is we use the electron groups and they repel each other strongly, and they're trying to maintain maximum distance among them, and that determines the shape of molecules. And first we talk about it's the shape of electron groups. So it's called electron group geometry. So going from n equals 2 is linear, n equals 3 is trigonal planar, n equals 4 is tetrahedral, n equals 5 is trigonal bipyramid, n equals 6 will be octahedral. With that, and that wraps up this podcast. Thank you very much for your attention.